Okay, very good evening to everyone, and welcome to the extra session of the NPTEL course Control Systems. So far we have gone through various problems on the topics that have been covered in the course. So we started from transfer function, poles and zeros, step response, and then how to draw Bode plot, Nyquist plot, root locus, etc. How to design a compensator. So based on all these topics, we have discussed a lot of problems. Now, apart from numerical problems or the theoretical problems, what else we can do? How to visualize these systems, or how to get these problems solved via MATLAB. So in today's session, we will see how can we draw a Bode plot, Nyquist plot, or how to write a transfer function in MATLAB, or how to write a state space model in MATLAB, and then whatever we have learned, that is gain margin, phase margin, etc., how we can visualize it using MATLAB. So let's start this session. Okay. So the very first thing that we will do today is how to write a first order transfer function. So let me write it first as, let's suppose we want to write a transfer function g1s which is equal to, we know in first order transfer function there is a maximum power of s as 1 in the denominator. So let's say that our transfer function is k divided by tau into s plus 1. So how can we write the transfer function in MATLAB? For that, let's first define our parameter. So the first parameter is gain k. So let's write k equals to, let's take it as 2. Any value we can take, and let's say the time constant tau equals to 0.5. I'm just taking random values. And then with these two parameters, we can define our transfer function g1 equals to, the command is tf, transfer function. And how we have to write it? We have to write it inside the brackets. So the first part is about the numerator. Since in numerator we have just gain k, so we can, and there is no s, so there will be only single parameter k. Separated by comma will be the denominator part. So in denominator we have tau s plus 1. So how we write? We write only the coefficients of powers of s. So the first will be the highest power. So highest power of s here is 1 and its coefficient is tau. So we will write tau. Okay. And the second and the power in decreasing manner. So we started with s to the power 1, then we have s to the power 0, and s to the power 0 has the coefficient 1. As you can see, we have 1 into s to the power 0, which will give you 1. So we can write tau 1. Okay, so this is how we write the transfer function. So if I run it, let me call it as first order. Okay, so if I run it, so semicolon, if you add a semicolon here, means in the command window you will not see any response. So to see the response, I will delete the semicolon. So as you can see, this g1, which is g1 here, is written as a transfer function 2 divided by 0.5s plus 1. Okay, so this is how we write the transfer function. Now Suppose we want to write a second order transfer function. Let's say we have a transfer function g2 of s. So if you want to comment any line, we just use this percentage sign. Okay, so g2s, let's say we have a general form of second order system, which is omega n square divided by s square plus 2 zeta omega n plus omega n square. Okay, let's say we have this second order transfer function. Now first we have to define its parameters. So let's say we take the natural frequency omega n equals to 5, and let's say zeta we take as an underdamped system, so we will take as 0.3. okay, and then so we have defined all the parameters, only two parameters we have. Now we will define the transfer function. We will name it as g2. We can give any name to it, and this is equal to tf. okay, transfer function. And so in numerator we only have omega n square, so we will write omega n square, and in denominator we have the highest power is s square and its coefficient is 1, so we will write 1. Then the power is s. okay, so its coefficient is 2 zeta omega n, so we will write 2 zeta omega n. okay, and then s to the power 0 has coefficient omega n square, so we will write omega n square. Now if I run it, you will see there are two transfer functions. So we have g1 that we have earlier defined, and then we have g2. okay, so this is how we write a transfer function. okay, and now suppose we want to write any general transfer function. So these are about first order, second order. Suppose I want to write a transfer function as any generic transfer function. So let's say we have a g3 transfer function bracket, and suppose we have numerator as 1 2, that means s plus 2. okay, and suppose in denominator we have s square, that is 1, 2s, that is 2, and 3, so that is 3. okay, now if I run it again, you will see that any random transfer function whose coefficient as numerator, in numerator we have s plus 2, and in denominator we have s plus 2s plus 3. So this is how the transfer function will look like. Now how to visualize or how to calculate the poles and zeros of the transfer function. So to see the pole of the transfer function, hello, my screen is visible to you? Are you able to see the MATLAB interface? Okay. So I was telling how we write a transfer function using MATLAB. So I started first with first order transfer function, okay, and then with a second order transfer function. And then any random transfer function we can write using the coefficients of numerator and denominator as G3. So this is how we write the transfer function in MATLAB. And suppose we want to see the poles and zeros of a transfer function. So suppose I want to see the pole of transfer function G1. So what we write? We just write pole G1. Okay. And similarly, if I want to see the zero of transfer function, I write G1. Okay, since the transfer function that we have taken, there is no zero. So if I run these two only, so you can see there is a pole at -2 and the zero is empty because there is no zero of the pole. Now suppose I want to see the pole of G2 transfer function, which is a second order transfer function, so there will be two poles, and so the poles that are coming for the transfer function G2 is complex conjugate and lying on the left half plane. Okay, so this is how we plot we see the poles and zeros of a transfer function. Now we have the transfer function, and suppose we want to see the step response. Okay, what is the step response of transfer function G1 or transfer function G2? Okay, so for the step response we have the command. So suppose I want to see the step response of G1. So let's first define for how much time we want to see. So let's say the total time t is 10 seconds. Okay, then for step response, so this is the step response. The command is step, and let's say we want to check the step response of G1. So it is G1 comma t end. Okay, for this much time we want to see. So let's run it. So here is the step response of transfer function G1. So you can see that for transfer function G1 we had a pole at -2, that is on the left half plane. So therefore we are getting a bounded response. Okay, so the response is bounded and it is stabilizing to the value 2, right? Now suppose I want to see the step response of G2. Okay, and we have seen that the poles of the transfer function G2 were complex conjugate, and those were complex conjugate and they both were lying on the left half plane. So the system should show a bounded response. Okay, so let's see what response we will get for G2. So yes, as you can see, the response, step response of transfer function G2 having poles on the left half plane but complex conjugate is stable. Okay, because it is getting stabilized to the value 1, and the zeta value that we have taken was 0.3, which is an underdamped system. Now let's say we take zeta as some greater than 1 value. Okay, overdamped system if we take, and if we run it, so what you will observe, it will show overly damped response. Okay, so because there is no overshoot here, there is no undershoot, so the response is overly damped and it is getting stabilized to the value 1. Okay, what about if we take the system as critically damped, that is zeta equals to 1, we will get this type of response. Okay, so this is how you can visualize the response of any transfer function. So as we have studied second order and first order transfer function in detail, so for second order you can see that for varying zeta, that is the damping ratio, the response is getting changed based on the value of zeta. Okay, so this was about the step response of a transfer function. Next we can see, yes, one more thing. In this step response, what we were seeing is only the graphical view. Okay, now suppose I want to know what is the maximum peak overshoot or the settling time or rise time. So let's start with the transfer function g1. So step response characteristics, if we want to see. Okay, so to know the characteristics, the command for that is let's take the variable name as info. So the command is step info, and say that we want to check the step info of transfer function g1, which was the first order transfer function. So let's run this. So here you can see that in the command window you can see that the info was the variable that we assigned for the information of the step response for the transfer function g1, and you can see that for this first order transfer function, the rise time you are getting as 1.0985 seconds, you are getting the settling time, you are getting the settling minimum, that is what is the minimum value for which the settling time is calculated, that is the step response value, and the maximum value of the band of the response for which the settling time is calculated, and there is no overshoot because of course it is a first order transfer function, there is no undershoot. Okay, so the peak value, that is the maximum value that you are getting, is around 2, and the time to reach that maximum value is 5.2729 seconds. Okay, so this is how you can check all the information of a transfer function. So let's also check for second order transfer function as well. Okay, let's change the zeta value to 0.5 on the damped system. Okay, so this is your step response. Now let's see what values we are getting for it. Okay, so the rise time is getting as 0.3278, which is very small. Again, settling time is 1.6. okay, so this is around here. So we are getting around 4% or 3% band in 1.6152 seconds, and the minimum and maximum value of the band is this. Overshoot is 16.29%. okay, the peak value is 1.16, so this value is your 1.16, and the time to reach this peak is 0.7184. so these are all the characteristics of the response. You can check using the command step info. All right. Okay, now let's move on to Bode plot. Okay. So, okay, now before Bode plot, let's see the root locus. Okay. Now what is root locus? Root locus is the locus of closed loop poles as gain is varied. Okay. Okay, let's start with our first order transfer function, and g1 we have already defined as a first order transfer function. So to see the root locus, we have to just write r locus, which is the command for root locus of g1. Okay, and we run it. Okay, so here is the root locus. Since we have only we have a first order transfer function, there is only one branch, and it is starting from open loop pole, which was at -2, you can see, and it is extending to -infinity as gain k is varied. So this is how you can interpret from the root locus, and the root is always going to be positive whatever the k is. So this is will be your root when k is 0, and then as you increase k, you can see that it is also showing you the value. So if you apply gain is equal to 1.22, your pole will be shifted to, your closed loop pole will be shifted to -6.86 value. Okay, so since it's a first order plant, so the damping is 1, you will not get any overshoot, and at that your frequency will be 6.86. So these are all the characteristics you can get from the root locus plot. Okay, now let's see for second order plant. Okay, for second order plant, we know we have two poles, so there should be two branches. Yes, so you can visualize from here also. We had the open loop pole at around some -2 complex conjugate. So you have the open loop pole at these cross point, and as you increase k, your poles are going to be complex conjugate always, and they will extend to infinity as k is increased to infinity. Okay, so whatever gain value you choose, you're always going to have your poles on the left half plane. Okay, because see here we have 0 here, so this part is the left half plane. So whatever the gain k we choose, we are always going to have a Bibo stability. Okay, so this we can interpret from the root locus. So let's check for the third transfer function, because in the third transfer function we took a very general type of transfer function where we had 1 0 and we had two poles. Okay, so let's see what type of locus we are getting for this. So yes, so as you can see, we had two poles. Okay, so the branches started from the here. Okay, and one branch is terminated to the 0 and the another is extended to infinity. Okay, and from here also what we can see is whatever the gain k is, we are always on the left half plane. So the plant response is always Bibo stable for any gain k that we give to the system. All right. Okay, this was all about the root locus. Now suppose okay, so we had our first no, let's say we had a second order transfer function g2. Okay. G2, let's again plot the root locus first. Okay, from here you can see that the root locus is coming like this, and let's say at any random point. Okay, so here your gain, let's take some So at this gain equals to 6, we have a complex conjugate pole at minus 2.5 plus minus 39. Okay, so what I'm trying to say is that, so this is the root locus of your second order transfer function. Okay, right now we have the open loop transfer function as g2. Suppose that I provide the gain to the system equals to 6 and I want to check the closed loop response. I want to check the closed loop transfer function. And if you provide the gain k and check the closed loop transfer function, what you will get, if you calculate the poles, you will get exactly as minus 2.5 plus minus 39, because this is what root locus is telling to us. For this open loop transfer function, if you provide gain k, your closed loop transfer function will have pole at minus 2.5 plus minus 39. So let's check if this really happens or not. Okay, so what we have to do, we have to take gain k equals to 6 and we have to verify whether the closed loop transfer function have poles of minus 2.5 plus minus 13j or not. Okay, all right. Okay, so let's choose gain k1 as 6. Okay, so we have to take the unity negative feedback, so we will write as the closed loop g1. So this will give us the closed loop transfer function of g1 with gain k1. So how we can get that? The command is to provide any feedback, we write the command feedback, and now with gain k1, our transfer function, open loop transfer function, will be k1 into g2, right? And we want to have a unity negative feedback, so we will write 1. If you want to have a positive unity feedback, you will write plus 1, but we are interested in unity negative feedback, so we will write as 1 only. So this CLG1 will give you the closed loop transfer function with gain k1 and unity feedback, negative unity feedback. So let's run it and see what is CLG1. So you can see that your CLG1 is this. Okay, now let's check the pole of CLG1. Yes, so the pole is exactly minus 2.5 plus minus, it is approximately 13. So this is what the root locus told us, right? So by visualizing the root locus, we have designed a controller K such that the poles of the closed loop transfer function, unity negative feedback transfer function, is shifted to or is made to at this pole location. Okay, so this is how we can design a controller to have a desired pole. So if someone asked us to design a controller K or the gain K such that the closed loop transfer function have this desired pole, so that we can check first by drawing the root locus and by checking if using a proportional controller are we able to get that closed loop poles, and then we provide that proportional controller K, so that will make the closed loop transfer function poles at the desired location. Okay, all right. Now next let's move to Bode plot. So the next part is Bode plot. Okay, so what does Bode plot do? it shows us the frequency, magnitude and phase plot of a transfer function. Okay, let's start with the first order transfer function first, that was g1. Okay, so for the first order transfer function, the command for the Bode plot the command for the Bode plot is, we can write for the plot as h, so we have to write the same as we call Bode plot. The command is Bode plot and I want to plot for g1, first order transfer function, right? Let's run it. So this is the Bode plot of the first order transfer function, which was this value. We had taken k as 2, so it is the Bode plot of 2 divided by 0.5 s plus 1. So this is a first order transfer function, and here if you want to get the characteristics of the Bode plot, what you have to do, so we can write as, let's say we want to know the gain margin, so we can write gm, any variable name you can write, phase margin, let's say we want to get the gain crossover frequency and the phase crossover frequency. So this variable name you can take whatever you want, and the syntax for this is margin for the transfer function g1. So margin with these brackets means that the first will give you the gain margin, second parameter will give you the value of phase margin, third will provide you the value of gain crossover frequency, and the last will give you the value phase crossover frequency. Just a minute. Okay, so these parameters will be provided if we write the syntax margin. So now let's run it. So here are the values for the transfer function, and this is the Bode plot for it. Okay, so for this Bode plot, we have the gain margin as infinity, the phase margin as 120, gain crossover frequency is not a number, and phase crossover frequency is 3.4640. So what is gain crossover frequency? So the frequency at which it crosses the zero, why is it NN here? Okay, let's check it for second transfer function. check it for G2. Okay, no, first we will plot for G2. So for the second order transfer function, what we are getting as the gain margin is infinite, phase margin is 90, gain crossover frequency is again infinite, and phase crossover frequency is 5. Okay. And then after Bode plot, we have already discussed root locus. Okay, now let's move to Nyquist plot. Similarly as Bode plot and root locus, okay, so to plot the Nyquist plot, the command we have to write is Nyquist for, let's say we want to plot for transfer function, first order transfer function. Okay, so this is how the transfer function looks like. We have seen that for a first order plant it was a semicircle if omega is varied from 0 to infinity, and if omega is varied from minus infinity to infinity, we have to draw the mirror image also, so it will give you a circle. So for first order transfer function, this is how the Nyquist plot looks like. Okay, so it starts at here for omega equals to 0, and omega as frequency is varied to infinity, this will be the real and imaginary part of the transfer function. And then if omega is varied again from minus infinity to infinity, so this will be the complete locus. Okay, for the second order transfer function, let's see how it looks like. Okay, so in the lecture also you must have seen that we draw it like we started at the value which is on the right hand side for omega equals to 0, and then we cross the imaginary axis, and as omega tends to infinity we get the value as 0. So this, as you seen in the lecture, is coming here in the plot. So this is how the Nyquist plot looks like, and this part is nothing, just the mirror image. So this complete locus will provide you the real and imaginary part of the transfer function as frequency is varied from minus infinity to infinity. Okay. Okay, so in Nyquist plot, now let's also see for the third transfer function where we had a 0 and 2 poles. So let's see how is the Nyquist plot for this transfer function. Okay, so this is how it will look like. It will start from here, and since there is a 0, it just goes to 0 via the imaginary axis, and then this is the a mirror image of the locus. So for the third transfer function where we had two poles and one zero, this is how its Nyquist plot looks like. Okay. Okay, now let's move to state space and transfer function. How we can move from transfer function to state space or state space to transfer function. Okay. Okay, so let's comment all this, or we can start a new program. Suppose we want to first write the system in the state space form. So for state space form, we need all the matrices, the state matrix, the input matrix, output matrix, and all. So let's say for a particular system, the matrix A is, let's say it is 0, 1 and -2, -3. Okay, sorry. So this is our matrix A. Okay, so in the first row we have the value 0, 1, and in the second row we have value -2, -3. So let me show you. Just a minute. Okay, let me rewrite the name of program. State space is already a function name, so we cannot write our program name as state space. So this is how the matrix A looks like: 0, 1, -2 and -3. Similarly, let's write the matrix P as the input matrix. So it is a column vector with values 0, and to write the value of next row we write semicolon. So this is our matrix P. So if you run it, you will see the matrix P is 0, 1. Similarly, C is a row vector and its entries are 1, 0, and let's say that D is 0. Okay, then to write the state space model, we just give a variable name to it. So let's say we have written a name for this as sys1. So this can be written as state space SS with matrices A, B, C and D. Okay, so if you run it, you will see that this system 1 have been allocated 4 matrices where your A is 0, 1, -2, -3, and it has taken the variable name which is a default in the case for MATLAB as x1 x2. So this is 0 1 minus 2 minus 3, and b is 0 1 and u1 because we have only one input because b is just a column vector and c is just a row vector, so only one output is there, y1, and then d is 0. So this is how sys1 stores the matrices A, B, C, D as the state space model. Okay. Now I want to write the transfer function of this state space model. Okay. So for the transfer function, since C is 1 0 means the output is y1. Okay. And since input is 0 1 means the input is x2. So if I write let's say the transfer function is GSS, we can write any name for it. GSS is the transfer function for this state space model. So we have to write TF, the syntax for transfer function, and our system is sys1. Okay, because sys1 is the state space model of ABCD. So let's see what happens if I run it. Okay, so you can see as per the matrices A, B, C and D, the transfer function is GSS, which is the transfer function of the state space model ABCD is 1 by s square plus 3s plus 2. Okay. So this is how we can convert any state space model to transfer function. Now if I want to go the reverse manner, so what I can do for it, suppose I have this transfer function GSS which is 1 by s square plus 3s plus 2. Okay. Now I want to get the state space model out of it. How we can do that? We just have to write sys2 equals to, I am calling the state space model for this transfer function as sys2, and this is equal to state space from the transfer function GSS. Okay. So as you can see, if you run it, we have for sys2, if the transfer function is GSS, the state space model for it will be ABCD as this. Okay. So using these command TF and SS, you can jump from state space model to transfer function or from transfer function to state space model. And you can check step response using any of these. Okay. Now suppose I have defined a transfer function, an unstable transfer function. Okay, let's call it as G, unstable as GU, and that transfer function, let's suppose, is, now another way to define a transfer function using a variable S is you first write whatever variable you want to take. So generally we take S as the variable of the transfer function. So we first define S as the variable of transfer function. So the command to define any variable as the variable of transfer function is, we have allocated S as the transfer function variable, right? So now we can just write the transfer function the way we write in paper. So it will be 1. So let's say we have an unstable transfer function. Unstable transfer function means at least one pole will be on the RHS. So let's say we have a pole at 1 and another pole is at 2, minus 2. Okay. Okay, so let's see what are the poles of this transfer function. So the pole of this transfer function GU is at -2 and 1. So since we have a pole on the RHS, the response should blow out, or the step response should go unbounded. So let's see if the response goes to unbounded or not. So let's plot the step response of this transfer function. So yes, as you can see, as time goes on, the step response of this unstable transfer function is going to infinity. Okay, so step response going to infinity means we provided a bounded input, because the step input is a bounded input. We provided bounded input, but the response that we are getting is of unbounded nature, so the response is going to infinity. Alright, so this is our unstable transfer function. Now if I ask you to design a controller so that this plant is will get stabilized, how we can do that? So let's first start with a proportional controller, okay, and see how we can stabilize the closed loop transfer function using a proportional controller. Okay, so for that, first let's plot the root locus. Okay, so the command is r locus for the transfer function GU. Okay, let's see the root locus. Okay, so the root locus, we can see that the root locus is getting started from the open loop poles at 1 and -2. Okay, and then as gain k is varied, or gain k is increased, it is getting shifted to the LHP. Okay, so this line is your partitioning line of LHS and RHS. So for this value of gain, what we can observe, if we click on it, at gain 2.9, our one pole is at 0.251 and another pole at gain 2.19 must be here. So it is at -0.743. Means if we choose the gain as 2.19, our closed loop poles will be both on the LHP, and the value of gain poles will be -0.743 and -0.251. Okay, and as we increase gain k, we will get critically damped and both our poles will be shifted to this value, because at here we have a breakaway point, so both the poles are same, and at gain of 2.25 we have equal poles of the value -0.5, around -0.5, and as we more increase the gain k, we will get a complex conjugate pole. So let's say we want to have both the poles real and on the LHP. So let's say we choose the gain as 2.2 to stabilize this transfer function or to stabilize this plant. So let's say we choose the gain k as 2.2. Okay, and we have defined a closed loop transfer function as GCL, which is equal to the feedback of what? Feedback of gain k into GU, which was our unstable transfer function, and the unity negative feedback. Okay, so this transfer function should have a pole both on the LHP. So let's check the pole of this closed loop transfer function. So let's check pole of GCL. So both these poles should be on the LHP. Let's see. So yes, as you can see, both our poles are on the LHP, -0.7236 and -0.2764. Okay, now if you plot the step response of GCL, it should be bounded. Okay, so let's plot both. So I'm going to plot both the step response, the unstable. Okay, so let's plot it for 5 seconds so that it can be visualized. Okay, here you can see the red one is the step response of the unstable transfer function, and now we have stabilized it using a proportional controller. Let me increase the value of time. So the blue one, if you see, is getting stabilized. Okay, so it is not getting unbounded. Okay, so this is how we can stabilize an unstable plant. Okay, so this is how we can design a proportional controller. Now, what about designing a PI controller for this? Okay, so let's take this transfer function and try to design a PI controller using MATLAB. Okay, so let me clear everything. Okay, so we have taken an unstable transfer function and I want to stabilize it using a proportional integral controller. Okay, so for designing a proportional integral controller, we need to get the value of Kp and Ki. So these value you can calculate by theoretical means using Routh-Hurwitz criteria, or by analyzing the pole location by calculating the characteristic equation, and then based on that you can get the value of Kp and Ki by solving the characteristic equation, which will give you the expression for poles, and from where you can get Kp and Ki. Another way is to just use the auto tuning method of MATLAB. So how this auto tuning works? So the command that we use for this tuning is the command PID tune. So okay, so I am interested in getting a PI controller, that is proportional integral controller, for it. Okay, so I will explain to you the meaning of this syntax. Okay, so what I have written is I'm going to use the PID tune command of MATLAB, and what does it do? We provide a transfer function GU. So we are interested in the unstable transfer function, and then I'm interested in designing a PI controller for it. So the PI controller designed using this PID tune method is getting stored as the transfer function PI, and all its characteristics are defined using the variable info. So let's run it and see. So let's give the name as PI tune. So if you run it, this unstable transfer function, it is possible to stabilize it using a PI controller. So stable flag is 1, means we are able to stabilize this unstable transfer function GU with value KP as 4.24 and KI as 0.105. So these values are getting from the auto tuning method, and we can further refine the performance by varying Kp and Ki around these values to further refine the response of our system. So from this way you can get the base value of your Kp and Ki and then further tune it to get the a better desired performance. Okay, now if you take these Kp and Ki values, which is getting stored as a transfer function named Pi. So if you write whatever name here, this is where the transfer function of the Pi controller is stored with this name, and this will provide you the crossover frequency of 1.4142 and phase margin of 18.4685. Okay, now so this means that if I write a closed loop transfer function as the feedback of Pi into GU. Okay, so I have applied the Pi controller to my unstable plant GU using a unity negative feedback. Okay, and then I am checking the step response of this closed loop transfer function. Alright, now let's run it. Okay, let me again run it. Okay, so your closed loop transfer function is written here as 4.24s plus 0.105 and this denominator. So for this closed loop transfer function, if you provide a step input, your response will look like this. So from here it is verified that the response is getting stabilized to 1. So the input we provided was 1 step input, so it is getting stabilized to it. So that means we are able to stabilize an unstable plant using the PI controller. Now in similar way, we can change the controller to PD and check if it is possible to design a PD controller for it. So for that we have to just change the PI to PD. Okay. So let's see if it is possible to do this or not. Okay, as you can see from the response that yes, we are able to stabilize it using the PD controller as well. And what are the parameters for it? Let's see. So to stabilize it, it is possible to stabilize it. We are getting 1 here. And the values of Kp and Kd, so this is how our controller looks like Kp plus Kd into S, and the values are 130 and Kd value is 11.9. Alright, and this is your closed loop transfer function, and this is how your response looks like. So earlier the open loop transfer function was unstable, it was getting unbounded when we provided a step input, and now this is getting stabilized to the value 1 as t goes to infinity. Okay, now similarly you can also use the PID controller. You just have to change this variable name, you can take anything, and okay, now let's see how it goes for PID. Okay, so with PID it is also possible. and the gain value, so the controller structure we know it is of the form Kp plus Ki by S plus Kd into S, and the tuner is providing us with the values 23.6 as Kp, 15.4 as Ki, and 9.01 as Kd. Okay, and we are getting stable, and these are the phase margin and crossover frequencies, and this is the step response. Okay, so this is how we can easily design a PI controller, a PD controller, a PID controller, or any controller using the command PID tune. Okay, okay, now till now we have only gone through the step response. What if I want to check the response of a system using, let's say, a ramp input? How we can do that? So let's see how to get the response with different inputs. Okay, apart from step input, if I want to check the response using the ramp or sinusoidal, anything. So for that, let's first again define, first clear everything, because we need to clear everything first, because all the things are stored in workplace. So if anyhow we mistakenly repeated the variable name, it will be overlapped with these values. So we need to first clear everything. Okay, and then let's say we first define the variable as tf for to use in the transfer function, and then we are interested in the transfer function, let's say a stable transfer function as 2 divided by, we can take as s plus 5. So we can call it as different input. Okay, so this is our transfer function. Now step input, if I want to see, we can get using the command step. So this is the step in response, and as it was clear from the prole location, the system is stable. So yes, it is getting giving us a bounded response. All right, now suppose I want to check the response for ramp input. So for ramp input, we know the ramp with respect to time is nothing but the function t, because it is in the ramp is something which is increasing with the argument. So here the argument is time, so the input should increase linearly with time. Okay, so for that first we need to define time. So let's say the time is uniformly divided in steps of 0.01 till 10 seconds. Okay, so this is what I mean. So if you run t, you will get the time as uniformly divided from 0 to 10 seconds, and the sampling period is 0.01. Okay, so this is how we have defined time. And input u we can call as t, because we are interested in ramp input, so we have defined the input as any variable u as t. Now the response y can be written as linear simulator. So we are going to simulate the linear system, and the linear system is our transfer function g here with the input u and the time response. Okay, now if I do that and then plot y, we will see the ramp response of this transfer function. Okay, so this is the ramp response. So as we all know that ramp is an unbounded input, it is not a bounded input, so the response is also unbounded for it. Okay, now let's change our input to some sinusoidal. So we all know that sinusoidal is a bounded input, so the response should also be bounded. So let's check it. So let's say that now our input is some sine function, sine of omega t, and let's say omega is 0.5 into t. Okay, we should get a bounded response because the transfer function is stable because it has pole on the LHP. Okay, let's see. Yes, we are getting. So let's plot it for some more time, for 100 seconds. As you can see, our response is always within a bound, and the bound is of minus 0.4 to 0.4. So y is always bounded between these two limits, and it is never going to infinity. Okay, so this is what Beaver stability tells us. If you have a pole strictly on the left half plane, so whatever bounded input you provide, your response is always going to be bounded, and this is verified from here. Okay, you can check it for any input. Let's suppose we are providing cos of 0.5 t plus 2. So this is also a bounded input. And again we are getting a bounded response. So in this way we can check the response for any transfer function. Now let's check it for an unstable transfer function having one pole on the RHP at pole location 1, and for this we are providing a bounded input, so the response should blow out. Let's check it. Indeed, as you can see, it is going to infinite value, some value which is 10 to the power 43. So it is getting unbounded. The blue curve, you can see it is getting unbounded. So whatever input you will provide, it will always and always blow up. So that's how you can visualize the response of any transfer function by providing any input to the system. Okay, so with this much syntax and with this much information, you can try one problem where you have a DC motor. Okay, you have a DC motor, and suppose I want to control the speed of that DC motor using the armature voltage. So there is a transfer function for it and also a state space model for it. Since we have dealt more with transfer function, we can start with a transfer function model. So suppose that you have a transfer function of the form output by input, where your output is speed omega and your input is armature voltage. Now you need to control the speed of that DC motor to a desired value. Okay, let's suppose 15 radian per second or 5 radian per second or 100 radian per second. How you can control it? Okay, how you can control it? Let's suppose using a proportional controller. That is the question. So based on this much understanding, you should be able to stabilize the system such that you are able to track the desired speed. Okay, so for that it will take a long time if I start from scratch. So I have written a code for this one. So suppose the motor parameters are defined as J, B, K, R and L as the standard variables, and then we can remove this part. We are not interested in load torque. Okay, so these are your A, B, C and D value, and then we have defined a system state space model, and we have defined the input as VA and the output as omega. Okay, and then we have the transfer function of this state space model as G. Okay, min real means the minimal realization we are taking. We can remove this minimal realization, or we can just take the transfer function. So for this state space of DC motor, we are writing the G min as the transfer function. Okay, and now we are interested in designing a PI controller. So since we have the transfer function with us already, we can design a PI controller for it using the command PID tune. Okay, so let's remove these things are not required. So we can design a PI controller, and then we have cascaded this PI controller with the motor using a unity negative feedback. Okay, and then these things are not needed. Okay, so we have designed a PI controller for the DC motor. Then let's plot and see what response we are getting. So suppose we have defined T from 0 to 2.5 seconds, or let's take it for 10 seconds. And then let's say we want our motor to have a speed of 100 radian per second as the reference speed. Okay, so R is 100 radian per second. Okay, and then we plot the results and we will see if we are able to get the desired speed or not. Okay, because for our closed loop transfer function with the PI controller, we are providing the reference as 100 radian per second, and then we have plotted the results. So let's check it. Okay, just a minute. Let me remove the unnecessary parts. As you can see, by the designed PI controller, we are able to track the reference angular velocity, which was of 100 radian per second, and this is the response of our motor. Okay, so this is how we can control the speed of DC motor using the PI controller, and these are the performance of the closed loop transfer function with the PI controller. So we have the rise time of 0.3683, settling time of 1.41, and all these things. And if you want to change the controller, you can do so by changing your controller here. So suppose I want to do that with a PID controller. Okay, so the PID controller will give you this type of response. Okay, So this is how we can design a controller for any physical system and see the response in simulation. Okay, let's stop here. So this is just these things are just the building blocks for designing a complete control system for any physical system. So first, what we have to do for any physical plant, first we have to write the mathematical model of that system using transfer function, or using state space model we can represent the system in MATLAB. And then first we will check if the plant is stable or not, so that we can do using by plotting the pole of the system. If we get a pole on the LHB, we need to stabilize it using a controller. So for that we will first plot the root locus, and in the root locus, if we for any k we are getting the root locus such that the poles are strictly on the LHB, we can be sure that using a proportional controller only we can stabilize the system. If not, then we move to any PI or PI controller, because if the root locus is never on the LHB, then a proportional controller cannot stabilize the system. So we need to move to PI or PID or PD controller for stabilizing the plant. And we can then design a PI or PID controller based on the performance we want using the PID tune command of the MATLAB. Now suppose we have another requirements also, that we need phase margin as this value, gain margin as this value. Then in that case we need to plot the Bode plot, and by looking at the Bode plot we can choose the compensator. If there is whatever the system is having, we want to have a particular gain margin or phase margin, then we can choose a compensator and then design a compensator by locating the pole and zero, so that the gain margin or phase margin will be the desired value. Okay, so this is how the whole process we can do using MATLAB and design a complete control system for a particular physical plant to get the desired response. Okay, so I hope this tutorial will help you in designing or visualizing the plant response or anything that you start your project with. Okay, so thank you for attending this session, and if you have any doubt you can ask. Okay, so wish you all the best for your exams, because the course I think is ended, and wish you all the best for your exam. And if you have any doubt you can ask using the comment section of the our YouTube channel, or you can also write an email. Okay, so thank you for joining this course and wish you all the best. Thank you.